Hey everyone, thanks for tuning in. Center of gravity is a term in physics that gets used in applied sciences in such seemingly unrelated and broad fields as motorcycle design and engineering, aircraft design, fixed wing or rotary, rigging and hoisting in the trades or wherever rigging and hoisting is used, shipbuilding, this is my deluxe boat here, and forklift operator certification, just to name a few of the fields that seemingly have nothing to do with each other, but alas, it is not so. Center of gravity is a concept shared by all of these, and this is not an exhaustive list of all the fields that use center of gravity, just a representative sample, or just a sample of a few examples. In this video I'll have more examples as we go along using these visuals. There's not a lot of math or no calculations to do. This is about explaining this concept of center of gravity through these examples, and as we go along I'm going to explain why this concept of center of gravity is so important and how it's affecting the design and daily operation or safety on the job for these fields where it gets applied. Let's get started with terminology. Center of gravity in course books, test books, guide books for forklift operator certification might be indicated with the letters CG, that's easy to print, or if the course book writers took the effort, they might use this symbol there for indicating the center of gravity in the middle of a load loaded on forklifts of a forklift truck, some such thing. So that symbol is used and CG is also used. The center of gravity is actually a term that's not too precise. It's a butchered and abbreviated term. Gravity is a force. It doesn't have a center, for a starter. Gravity as a force has a direction in which direction it acts, and it has a magnitude, such as 5 newtons of force port side, whatever, east. It has a direction and a magnitude. It doesn't have a center. Now, center of mass might be more intuitive. You can imagine the mass of something, a mass of motorcycle, and mass centralization is such a concept in motorcycle design or aircraft design. Well, mass can be somewhat centralized, but the center of mass or center of gravity is not mass and is not made of mass. So these two expressions or terms are somewhat imprecise. A better one would be, with more words inserted, would be center of gravity could be visualized as a center about which the object balances, or center at which gravity seems to act on an object. So in case of a motorcycle, somewhere here in the heavy engine, somewhere here is its center of gravity, somewhere, depending on the design, could be lower, could be higher, could be a little bit fore or aft or wherever it is, depending on if it's a full tank of gas or whatever. A center of gravity could be visualized that it's a point in the motorcycle at which gravity acts on this motorcycle and pulls it down or sideways, whichever the case it is, whatever the vehicle is actually doing. Same for aircraft and same for ships. Now, one good working definition for center of gravity, so we can insert all of these words, that center at which, or a point at which gravity seems to act or acts on an object. But another working one that I'm going to be using often is this center of gravity is a point at which an object balances. And this is really easy to conceptualize and envision with just a paper and a pencil. If I drew a square here, or a rectangle, or any kind of two-dimensional polygon, whatever, regular or any kind of polygon on the sheet of paper, let's go with a rectangle, and if I drew its diagonals both ways, where the diagonals intersect, that's where its center of gravity is. It's easy to see it if you cut it out from the paper. Now it's going to be not a 2D shape, it's going to be a 3D shape, and if you put it on your fingertip, it's going to balance at the intersection of the diagonals. So that's where a rectangle's or a square's center of gravity is. You can do this with a regular pentagon or whatever, a star, other regular shapes. We can do this with a little thicker material. Over here I have another rectangle-ish looking thing. Of course it's got batteries in it. If I drew the center or the diagonals of this one, at the intersection of the diagonals, this object of course doesn't balance because the batteries are heavier on one side. You can find very, very easily the center of gravity at any object. Just find a point where it balances. Very straightforward. Somewhere there between, I don't know, the top battery and this one in the bottom. So somewhere in the middle is its center of gravity. It balances there. Very straightforward. You did this when you were a kid. If you put a pen, find its halfway point, it's not going to balance there because the cap is heavier. So you're going to have to shift it just a little bit towards the cap. Eventually you'll find a point where it actually balances. Just give me a sec there. It's a little bit overdone there. Yeah, it works like a seesaw or teeter-totter or whatever market, wherever you grew up with and whatever terms you used. So there it balances. It's very easy. Exactly the same. This is just one way to find the center of gravity. There are other approaches, geometric, and you can also suspend items to find their center of gravity. That method is really important for hoisting and rigging, comes up later. But for now, we're just going to stick with this one. So it's a point. Center of gravity is a point, a fancy name for a point at which an object balances thereabouts. Now, the center of gravity, I have four important things about center of gravity. One, I indicated that this is not really a center of mass. It's not really a center of anything because gravity doesn't have a center, and also the center of gravity is not made of mass, not made of material. It's not made of matter. And this is what I have in mind. Here is a rectangular prism. Okay, we'll call it a wooden block. Here's a wooden block with an assumed uniform density. Yes, it's missing a sliver. Don't worry about it. You can still find a point at which this balances, just like we did with a pack of button cell batteries, there in the middle. Now, the center of gravity is inside there in this wooden block. But if I drill a hole at the intersection of this rectangle here, drill a hole there and push this dowel out of it, the center of gravity is still there. The center of gravity is not made of wood. The object now lacks wood around its center of gravity plus some generous distance, and it still balances around that one point. That one point is there in the middle, and it's not made of air either. You cannot balance a block of wood on air. You balance it on your finger, but the center of gravity is not made of air either. The center of gravity's size is a point size. Point is a theoretical size. It doesn't have width, length, or height. It only has a location. Its location is there at the very center of that hole about which this object balances. So my first important note here about the center of gravity, besides the definition, is that a center of gravity is not made of matter. Number two, the center of gravity, however, is real, and it is a single point. Okay, we're going to get to the single point. In this orientation here, the axis is this vertical axis of the object. On another face of this rectangular prism or block of wood, if I drew the diagonals again, another hole can be drilled, such as the case with this one here. And of course, if I take out the dowels, it still balances about the same point there. So its center of gravity is still there. If I take out the first dowel, center of gravity is still there, a single point, tiny, tiny point. And if I get these dowels out, the center of gravity is still at the intersection of where these two bored holes intersect. One vertically and one transversally. This is important, that at the intersection of these two axes is where the center of gravity is on this block of wood rectangular prism. So this axis, this vertical axis, if this was a vehicle, this would be an axis of yaw, or this was an aircraft, this is a yaw axis, and this is its transverse axis here, about which the object pitches up and pitches down. Okay, so that's two axes. The intersection of it is a single point that's so tiny it's not even microscopic. It's so small that it's theoretical. Nevertheless, it is real. It's there. Around that point, this object solidly balances. Of course, the concept can be extended into three dimensions. You can still see probably my pencil marks there on the end grain of this block of wood. So there you have a longitudinal axis, a transversal axis, and this vertical axis for yaw, pitch, and roll. Obviously, all of the objects, motorcycles, are also all affected by roll, pitch, and not so much about yaw, but the third axis, the yaw axis, goes through the fuel tank there, somewhere roughly. This is just for concept, okay? So where these three axes intersect on a motorcycle, that's where its center of gravity is, somewhere inside the engine, but it's not made of engine, it's not made of metal, it's not made of air, it's not made of wood, it's just there. If I continue with the concept, you see where we get to. This is our laundry item. Its center of gravity is there in the middle, where all of these axes on this sphere intersect a single point, and it's not made of air, around which the object will balance, if I can balance it. You get the idea. So this real center of gravity is often in a ship is inside the cargo hold. This skewer here, this bamboo skewer, is its longitudinal axis about which the ship rolls, port and starboard there. So we're trying not to list to either sides, but you get the idea. This balance is this way, and if I made the intersection transversally, you can see the hole through there, and probably you can see the bamboo skewer through that hole thereabouts. And the intersecting point is somewhere here. That's where the center of gravity of this vessel is. It is possible to go down from the deck, go down into the cargo hold between, I don't know, decks 2 and decks 3, somewhere at chest height, midship somewhere, maybe towards, depending on how the ship is built, somewhere you will find at chest height the center of gravity there. Ideally along the longitudinal axis of the ship, somewhere, I don't know, 4.5 stories above the keel. Okay, I hope that makes sense. Of course, you can't hug the center of gravity. There's nothing, it's not made of air, but around that point, and it's not this big, it's not this big, it's not this big, even the center of gravity of a huge ship is just a single tiny point about which the whole vessel balances. And it really is important that when you set sail, this be on an even keel, not listing to port, or not having a trim by the head, or okay, same stuff applies for aircraft, but it's fixed wing. If the center of gravity is not considered carefully, and the helicopter is tail heavy, or aircraft is tail heavy, as soon as it leaves the ground, it's going to pitch up because the center of gravity is going to move. So that's my next point. The position of the center of gravity profoundly affects handling. Okay, that means that so an aircraft can take off pitched up because the airflow is going in this direction. On a wing or on the blades, you can't have lift going this way if the airflow is this way. It's not just going to go up that way. It's not happening. Same way, if it's nose heavy and if it pitches down, it doesn't really fly well this way. For the wing to generate lift, it has to have a pitch angle of certain degrees. I want to avoid numbers intentionally here. That's the way a wing works and generates lift. On a motorcycle, this angle isn't so important, but it does have to balance side to side. If you replace the exhaust for an aftermarket exhaust, the original design considers listing on a motorcycle. If this becomes lighter and now the vehicle is heavy to the left side of the vehicle, it's going to be more difficult to balance it. It's going to be it's likely to give the rider an unbalanced seating position or sitting position, and it's likely to load one shoulder differently than the other. It's going to get you a neck ache or headache or whatever. If your vehicle is uncomfortable, it might be, I'm not saying it's 10 degrees listing to port, but it might be half a degree or 1 degree enough to engage some of the muscles that need to balance this vehicle back to vertical, or if you made one side intentionally lighter. How you can check it on a motorcycle, of course, is suspend it by 2 lines and see which way it tilts. But of course, rigging and hoisting, I'm not saying suspended by the windshield or suspended by the, but it has to be suspended along its longitudinal axis somewhere, exactly. So it's not something you could actually do. It's not really doable or feasible in your garage at home just because you have a rafter overhead and some chains and ropes. All right, but so just as a modification or design consideration, if you start shifting around the mass on the motorcycle, its center of gravity is going to be affected. Likewise, if you put a load here to port side on top of the deck, the ship is going to be top heavy. That's one thing. Here the ship is going to be bottom heavy. So of course the ship is going to lift to port immediately as soon as the load is landed on the deck. It's obvious with a ship. It's less visual or less obvious with a motorcycle, and it's less obvious with an aircraft because you can't see it while it's on the ground. It might be compressing the tire on one side a little more, but just like I don't know, a few millimeters, whatever, half an inch. Once it's airborne, it's immediately becomes obvious. Once it has no pavement for supporting and distributing its weight, that it's lopsided and it's going to be tilting to port or whatever. So the center of gravity profoundly affects the behavior of the vehicle. Same with forklift or rigging and hoisting. If you lift this load up by 2 lines, you lift it up, this center of gravity will move immediately and swing. So those people around it who stand around, they can get, that's why you put a tag line or a guy line on a load, so you can control this swing when it's being picked up from the ground. Also, a good crane operator rights it first before picking it up. Doesn't just, if the hook is overhead here, doesn't just yank it up and swiping people out on this side with the swinging load and shock loading the crane and everything. So center of gravity profoundly affects load behavior, vehicle behavior, and vehicle handling and load handling as well. My last point that I want to make here real fast is that the center of gravity can also move, add, and combine. The center of gravity of this block of wood will remain with it, and the center of gravity of this block will remain with it. Once they are combined like so, a third center of gravity, independent of the previous 2, will appear halfway between the 2 of them, somewhere there, and they will have 3 centers of gravity. But the 2 items combined will behave and balance around the latest 3rd center of gravity. Motorcycle plus rider. The rider has its center of gravity wherever that is in seating position. I don't have a mannequin to put it on this motorcycle, but you get the idea. And the guy is going to shift side to side and fore and aft as the motorcycle is being ridden. Their combined centers of gravity, one on the motorcycle and somewhere here in middle of torso, somewhere here for the rider. These combine together to be a 3rd center of gravity. Of course, also depends on how much gas is in the fuel and everything else. And the motorcycle and rider combined will balance around this new center of gravity. This new center of gravity could be in mid-air, not in the motorcycle, not on the motorcycle, could be in the air between the motorcycle rider and the motorbike, just like a combined center of gravity between this piece of cargo on deck and the ship overall could be somewhere here mid-air, midship, at chest height, in thin air, below the deck. Okay, I hope that makes sense. So the center of gravity can move and is expected to move, especially and depending on how vessels are loaded, or motorcycles, vehicles, trucks, cars, helicopters, aircraft is loaded. The center of gravity can move if the load moves. That's why securing the cargo is of utmost importance. So this should be tied down, and even if it's tied down and it's liquid cargo inside, center of gravity will still move and slosh about in it, further affecting, exaggerating lift or heel if if the vehicle is in a stormy condition. So affecting aircraft tossed about by the winds, same thing. Can be really, really bad, can capsize a vessel, can bring down an aircraft, and can cause a crash really, really easily. So I'm not going to redesign your motorcycle. I'm not going to tell you which modifications will cause how much shift in the center of gravity. That's why I avoided numbers. And this is a 20-minute video, not a 4-year degree in naval architecture or motorcycle design or industrial design or aircraft design. For that, you need to go to college. This is just an explanation of the concept and an overview of it and why this is so important. Thank you very much for watching. If you have questions, comments, put them in the questions or put them in the comments box below. I'll try to answer them as fast as I can. Thank you. Bye-bye.